Okay, so ASIO is an acronym for Audio Stream Input Output. So this is a driver level software for transporting digital audio between Windows applications and audio devices. This was developed by the Steinberg Company of Germany in 1996, and so it's a way of using audio in Windows computers that is has a direct path to the audio system. It doesn't go through this Windows mixer. It offers low latency, and there's no signal degradation. And it has become a de facto standard for use with professional audio devices that are used on Windows systems. So things like mixing consoles, all sorts of audio devices use this interface. So in APX, what we've done is we've implemented a connection to these ASIO devices. And what you can do is, in our software, you just go to the list of input connectors and output connectors. And if you choose ASIO and you have an ASIO driver installed, the device just shows up as another physical connector, even though it's not a physical connector. So this ASIO connector selection allows APX to access pro audio equipment that has an ASIO driver that's connected to the PC running APX 500. The connection between the PC and the audio gear may be over a variety of interfaces. So typically they're USB or FireWire. It can also be Ethernet, MADI, CobraNet, or Dante. And as I mentioned, typical devices include mixing consoles. There are also microphones, speakers, and PC audio interfaces. So in the APX software, you just choose the connector as ASIO, and if the device is installed, it will show up as a device on the computer. Same thing on the So on the output or the input, you can choose ASIO. Then you would simply choose which output channels you're going to use. Now, one of the advantages of this is that even on a 2-channel audio analyzer, you can connect an ASIO device that has many, many more channels. And in our software, we can analyze up to 16 channels at one time. And you can choose which channels you want to be included in the analysis. You also have a button here in the software that launches the control panel, and that opens the control panel for the ASIO device that's usually supplied with the driver. And then we have this device info panel where you can look at the input and output buffer sizes, and also the control over the buffer size. The ASIO device will often have settings for sample rate, clock source, and channel configuration. It may also have settings for latency and buffer size that can be adjusted for optimal performance. Any latency in the device can be accounted for by entering it in the APX. There's a field inside this software called the device under test delay, which accounts for a delay between the input and output. So for example, if you generate a chirp and there's a delay of so many milliseconds in the device, you can insert a delay that will wait that long before acquiring the input signal to compensate for this delay. And we can measure the delay using measurements like acoustic response and continuous sweep. This is a flow diagram of how it works. So this box here represents the Windows PC that's running the APX software. It's also running the ASIO driver for this device that's connected. The device is connected over some interface like USB or FireWire or Ethernet, etc. And then the APX software connects with the instrument over USB 2.0. And inside the PC, the ASIO client within APX communicates with the ASIO driver for the device. And then we can connect our analog outputs to the device's analog inputs and vice versa. Same thing with the digital outputs and digital inputs. So this is really, it's a software interface, but the way it's implemented in our software, in APX 500, you must have an analyzer connected. The reason that we do that is if we allowed you to connect to our software without an analyzer, it would be like giving away a free audio analyzer, and we don't want to do that. One of the advantages is ASIO compliant audio interfaces can be tested directly on the PC running APX 500. We currently have sample rates from 32 kilohertz to 192 kilohertz. And as I mentioned, you can have up to 16 channels of input and or output. So if the device supports it, and if there's a use case for it, you can actually generate over ASIO and analyze back in over ASIO at the same time. In most cases, you will be going out ASIO and then coming in some different interface or vice versa. This is, it's standard included in our APX 555, 525, and the 585 series. And for the 515, which is intended for production test or entry level, it's an optional upgrade. So there's really not much to it. I'll do a little demonstration here. So what I have for a device is, this is called a Mackie Onyx Blackjack. It's a 2-channel USB audio interface that has an ASIO driver. And it's currently not connected via USB. So let me flip over to bench mode here. And if I choose, let's see, I want to go, yeah. If I choose ASIO, I get a warning indicating that nothing is connected. And in my list of devices, there's nothing connected. So let's see if I can do this without restarting the software. I'm going to plug in the USB cable to this device. And this is just connected to one of the USB ports on my Windows computer. Now if I choose, if I choose ASIO, there's still nothing connected, but it shows up as the Mackie ASIO driver. So when I select the device, now I can choose this settings panel. The title here is Mackie ASIO driver settings. So the sample rate is 44.1 kilohertz. The buffer size is 2,048 samples. The clock source is the computer. There's no other choice at this point. And dither is enabled by default. And if I look at this control panel, this should launch. Yeah, it launches a control panel, which is over on this other screen. Let me drag it over there. And it's a very simple control panel. It just shows the device stream formats, the mode. So it's in safe mode currently. There are different modes available, like minimum latency, low latency, standard, relaxed, safe, and extra safe. And then you can choose a buffer size. These vary from 64 samples up to 8 kilosamples. And let's see here. So in this case, it's only mapped one output channel. I can choose a second channel here and add it. And I believe you can also change the order of these, so I can map channel 1 of my output to channel 2 of the device's output, and so on. And if you had multi-channels here, you could just add up to 16 of them at a time. That's the current limitation in the APX software. You can also choose to enable or disable dither. So let's go ahead and turn on the signal here. We're generating a sine wave at minus 20 dB. Oh, and we have to choose our input. So this has balanced inputs. Actually, I'm doing this the wrong way around. Yeah, these are mic inputs. So I need to be connected. I need to be balanced out and choose ASIO on the input side. And I can configure the channels again. Okay. Let's go ahead and turn on the signal here. So as you can see, it generates a sine wave. We're looking at the RMS level, and I think there are some gain pots on here you can use to change the gain if you wish. So that's pretty much all there is to it. So here we're looking at the distortion in dB. We can gradually increase the level here. So let's try a little test on this device. Let me go. I'll do what's called a stepped level sweep. So we'll leave the generator at 1 kilohertz, and let's do a sweep of generator level from 1 millivolt to 2 volts RMS, and by default we're looking at the RMS level. Let's also look at the distortion, THD plus N ratio, and we can check also linearity. So let's have a look here. So this will gradually increase the sine wave, which is at 1 kilohertz, from 1 millivolt to 2 millivolts, sorry, 2 volts RMS in 31 steps that are logarithmically spaced. There we go. So for a linear system, this should be a perfectly straight line. And if we look at the linearity graph, it should be flat at 0 dB. Quite often when you get up to higher signal levels, the system will become nonlinear and you'll introduce a large amount of distortion. So here is the THD plus N ratio. Can change that to decibels. The T here indicates that there's a timeout on settling. So the analyzer uses settling algorithms to make sure that at every step change it's getting good data. Looks like we could go a little further here, but you can see the THD plus N starting to rise. So if we go back to the monitor's display, you'll probably see, so we were at 2 volts. You can see a lot of distortion components coming in here, and probably not too far above here. It's going to, yeah, so huge increase in distortion at 2.5 volts. So if we had gone just a little bit further beyond 2 volts in the sweep, we would see this curve spike up by a large amount. Actually, maybe I'll redo that. Why don't we just go to 2.5? And I wonder if the lack of settled readings might be because I was playing around with the displays during the test. So that's basically it for ASIO. It's very simple. Once you have an ASIO device connected, it just shows up like a connector in the APX software. Are there any questions on that? This is it's a very powerful feature for us because it gives us access to other digital interfaces. So recently we published an article on using Dante devices through an ASIO driver. We're also looking into other solutions such as AVB. There you can see the large spike in the THD plus N level, indicating clipping. So HDMI stands for High Definition Multimedia Interface. It's a standard for audio and video transmission between a source and a sink over a single cable. It provides for high-definition video up to 1920 by 1080p at 60 hertz and 48 bits per pixel, and high-resolution audio up to 192 kilohertz, 24 bits, 8 channels uncompressed. So this is the current, well, I guess this is the HDMI 1.3 and 1.4 standard. HDMI 2.0, of course, is going to have higher channel counts and higher sample rates. So HDMI is the standard on most new consumer AV equipment. If you bought an AV receiver or a television in recent history, it's definitely going to have an HDMI connection on it. So in the APX software, we cover HDMI specification 1.3a, and we also cover audio return channel, or ARC, and that's a feature of the 1.4 specification. The only other changes to 1.4 did not involve audio, so we're pretty much compliant, but we don't handle some of the higher video bandwidths that are included in that standard. So we talked about the connectors this morning. There are 3 connectors, Type A, which we have on our analyzer, 19 pins. This supports standard definition TV, EDTV, and HDTV. The Type B has 29 pins intended for future expansion, and it's not generally used. And then Type C, a 19-pin mini connector for portable devices, which can also be connected to the Type A connector. So HDMI has a huge bandwidth, up to 10 gigabits per second on the TMDS lines. And TMDS stands for Transition Minimized Differential Signaling. So it's a high-speed interface used for video and audio. This is needed for high-resolution video rather. And the video transmission method is identical to DVI. So DVI, or digital video interface, is just like HDMI without the audio, essentially. You can buy a cable or an adapter to convert between HDMI and DVI, and it works fine. You just don't get any audio. So the audio and what we call metadata are contained in data islands, or packets that are inserted into the stream during blanking intervals. So you can see here's a stream with 858 total pixels. There are 720 active video pixels, and then these horizontal blanking intervals of 138 pixels. And the audio will get inserted in these islands between the active video. At high video resolutions, there's plenty of bandwidth for high-resolution, uncompressed audio, lossy or non-lossy compressed audio, or 1-bit audio, DSD, or direct stream digital. Audio capabilities are reduced at low video resolutions, lower sample rates and channel counts. So one thing that's quite different between HDMI and the other standard digital interface like AES-3 and SPDIF is that the audio clock is not transmitted over HDMI. The clock is derived at the sync end from the video clock. So the source computes these values N and CTS such that 128 times the sample rate is equal to the frequency of the TMDS clock times N over CTS. So N is fixed for a given video and audio rate, and there's a lookup table. The source counts the TDMS clocks per audio clock to determine what the CTS is. And N and CTS are transmitted in what's called the audio clock regeneration packet. So the clock is regenerated at the other end from these values N and CTS. So asynchronous video and audio clocks, or audio clock jitter, can cause CTS to change over time. Now the audio packets use what's called LPCM, which stands for linear PCM, pulse-coded modulation. And this follows the IEC 61937 standard. It's formatted very similarly to IEC 60958. And so they use 28-bit words, up to 24-bit audio, plus these VUCP bits, validity, user, parity, and what was the other one? Channel status. And there's also a 192-bit channel status block encoded. So it supports up to 8 channels of linear 24-bit audio at 192 kilohertz sample rate. It also supports IEC 61937 up to 6.144 megabits per second. That's 16-bit words at 192 kilohertz frame rate. So the IEC 61937 is encoded audio like Dolby Digital Plus, DTS Digital Surround, or DTS HD High Resolution. And these are quite often used on Blu-ray players, for example. It's also used for lossless compression schemes. So Dolby True HD has a maximum of 18 megabits per second, and DTS HD Master Audio has a maximum of 24.5 megabits per second. Blu-ray discs have the capacity and bit rate to support these formats. Many current implementations decode in the player and they transmit linear PCM over HDMI. And AV receivers have decoders built in. So in the APX platform, we can generate these encoded audio streams and we can record them, but we do not decode them. Now this audio metadata is sent at least once per 2 video frames, and some of the information is already in the audio stream. So we have the IEC 60958 channel status, the sample size and sample rate, and the IEC 61937 burst info. That's the coding format. So some information about encoded signals. The audio info frame adds extra information on the HDMI interface. So we have the speaker allocation for linear stream. So if you have multi-channel audio, it'll tell you which channel is the front left and the front right and the side surrounds and so on. There's also a level shift value for down mixing, and there's a down mix inhibit for DVD audio. Now what about jitter over the HDMI interface? Well, potential sources of jitter are jitter in the source audio clock, jitter in the source video clock, asynchronous audio and video clocks. This can cause CTS to change over time. Or poor performance of the sync phase locked loop. Now, we use the Silicon Image 9134, 9135 chipsets, and we've found that the receiver-transmitter pair is highly resistant to jitter. Injecting even high levels of jitter into the source audio clock produced no measurable jitter at the receiver. So we don't really think it's an issue over HDMI. There's also the concept of EDID, which stands for Enhanced Extended Display Identification Data, a data structure supplied by the sync device. So when you connect a series of HDMI devices together, the end sync device informs the source of its rendering capabilities. And that includes the video resolution and the interlacing, the video frame rates and the color space that it supports, and the number of audio channels and the types of compressed formats or encoded formats that it supports. This enhancement of EDID was devised by the VESA for computer displays, and the EDID is transmitted over the display data channel, which is one of the lines on the interface. When the source and the sync are connected, the source powers the EDID ROM inside the sync and reads it using what's called I2C commands. So these are, it's an interchip control interface bus that's used to read this EDID value. So the source is responsible for supplying data to the sink in a form that the sink can handle. This might include down conversion of video or decoding, downsampling, and downmixing of audio. The EDID is probably responsible for most of the HDMI problems. So in the early years of HDMI, we went to a number of these HDMI plug fests. That's where manufacturers from all over come and they test their devices together. And we found that problems with the EDID were one of the most frequent causes of problems between devices not being able to work. So the sink may not be supplying a truthful EDID. In other words, the TV might say, you know, I take encoded audio like Dolby Digital, but it might only accept 2 channels of audio. And the source device will play the encoded audio, and of course it won't work. It'll sound terrible because it's not audio. On the other hand, the source may not be interpreting the EDID correctly. The interface also supports the Consumer Electronics Control, or CEC, and it shares control information among all HDMI connected devices. So this allows devices connected by an HDMI cable to be controlled by the same infrared remote control. They share common commands. So you have convenience features like one-touch play and record, automatic source switching, timer programming, system audio control. It's a single line connected to all devices in the chain. There's automatic address recovery, and there are dozens of message types that can be transmitted. HDMI signaling. So the audio video metadata is 3 TMDS transition minimized differential signaling data channels and a TMDS clock channel. The clock rate is a multiple of the video pixel clock rate, and the audio and metadata are sent during video blanking intervals. The audio sample rate can be asynchronous to the pixel rate, and as we mentioned, the audio clock is regenerated at the sink. There's the DDC, display data channel for configuration, and the sink informs the source of its AV capabilities. And then the optional CEC, or Consumer Electronics Control Line, for passing remote control information. There's also HDCP, high bandwidth digital content protection. This is an authentication and encryption scheme used by HDMI, DVI, and DisplayPort. So all HDCP compliant devices contain 40 56-bit keys. The source will initiate authentication by sending a 40-bit key selection vector, KSV, to the sink. The sink responds with its own 40-bit KSV. If the sink's KSV is on the revocation list stored on the media, the source will not proceed with authentication. The source and the sink compute identical keys using counterparts KSV. Pixels get encrypted or decrypted with these secret keys, and the keys are updated each video frame. HDCP is probably the next most common result for HDMI trouble. And then there's HDCP repeater problems if you try connecting devices directly. So in the APX software, we have the ability to enforce HDCP, to enable it or disable it. We can also record audio streams from HDMI devices, but if they're encrypted, we can't record them. We're not allowed to by the HDMI standard. And this is one of the problems we've had with a lot of Blu-ray player manufacturers. They've asked us why we can't record the audio from their Blu-ray. And the problem is that most Blu-ray players enforce HDCP, and we're not allowed to record a stream if it's turned on. This shows the HDMI routing within the APX software. So there are 4 ports on the front. There's the source. So this would be the source sending out audio and video. And then there's the sink on the right, which is the input. So typically the source is connected to a sink, a device under test, and the DUTS source is connected back to our sink. Inside the instrument we have a loopback for audio, so we can generate a signal out of our source and analyze it on the sink. We also have the ability to send EDIDs and get them back, and we can also send and receive CEC commands. We have a second port here, which is typically used for can be used for a video generator. So I'll show you in the software we can generate very simple video patterns like a solid color. But if you wanted to hook up a video generator, you could hook it up into this port. Then we have an auxiliary out port, which is usually connected to an HD TV. So you can use the TV to look at video signals while you're testing the audio. And then when we get into ARC, the use of these ports, ARC being audio return channel, the use of these ports changes, and we'll talk about that a little bit later. So the APX HDMI hardware can generate and analyze 2 or 8 channels of linear PCM at 24 bits, up to 24 bits and 192 kilohertz. It can output pre-encoded audio waveforms in Dolby and DTS formats. It has switchable HDCP encryption and automatic decryption. And as I mentioned, it has the aux input for video pattern generator and the aux output for a video monitor, but neither is required for correct operation. So you can see a typical use case here. We have the HDMI signal here. This is a HD receiver, and we can generate from our source into the sink, from the source of the device back into our sink, and then we can optionally take a video generator into the video input here, and we can monitor the output on a television. So in our software implementation, you can choose the output and input connectors to be HDMI source output or HDMI sink input. You also have access to an EDID viewer. And then, of course, you can choose the audio format. So layout 0 is linear 2-channel PCM. Layout 1 is linear 8-channel PCM. You have access to the sample rate and some settings. The HDMI source settings panel has additional controls for bit depth and dither, so you can set the bit depth here and enable or disable dither. You have some control over the N and CTS values. You can set them to auto, which we normally do, or you can manually set N and CTS. With video, you can choose to pass through an external video if you're using a video pattern generator, or you can generate a simple pattern like a color. You can also choose the color bit depth here. We can enable HDCP encryption, and you can access status and user bits in the audio info frame. Just like we did on the AES3 interface, you can do on HDMI, but there are some additional parameters for the audio info frame. The HDMI source EDID viewer, so we're able to look at the EDID of the source, and the main things that we're interested in audio are the CEA audio data block. If you drill down into this, you can see the short audio descriptor 1, and this tells us that the sync device is able to accept linear PCM and only 2 channels. So this is probably a television that we're looking at here. On the input side, or the sync side, Here are some of the controls. So you can control the audio bit depth. You have some controls over the sync EDID. So you can use our default EDID, the one that ships with APX. You can use the EDID from the device, the television or monitor connected to our aux out, or you can use a custom EDID. And if you use a custom EDID, it opens this panel called the EDID editor, and here you can go in and you can actually change the short audio descriptor. So for example, if you want to force the device to tell you that it can handle 8 channels, you could change it from linear 2-channel PCM to linear 8-channel PCM, and so on. And then we have some control over the CEC. We have some monitors and meters that are useful for HDMI. So there's the metadata monitor, and this looks at some of the metadata that's embedded in the HDMI interface. And we can also control the CEC. So we're able to send CEC commands from and to, and we can choose operation codes and send a message. So this enables you to test some CEC devices that are on the bus. There's also an HDMI status bar, so the green on black indicators at the bottom of the software, you can see the HDMI output. This tells you the layout and the audio sample rate. On the input side, you can see the layout, the signal type, whether it's PCM or encoded audio, and the input sample rate. This is a typical configuration. So this would be testing a play-only device like a Blu-ray player or a disc player. So here you have the player. You would need a special disc that has some audio signals on it. The signal comes out of the source into our sync input, and then you could monitor the video on a TV installation. So this is an application where you really need one of these video monitors, because typically with a Blu-ray device you'll get a remote control that you can use to choose from a menu, and to be able to see the menu you have to have a television in order for the menu to be displayed. Here's an example of testing a receiver. So here we would be going HDMI into the receiver from our source into the input. We would look at the output of the receiver for video on a monitor, and then we would come out the analog outputs from the receiver into our unbalanced analog inputs. And our 8-channel instrument, the APX 585, is very popular for this because it has 8 channels of analog output and 8 channels of analog input. So with an HDMI interface, it's quite a powerful tool. This is an example of testing a receiver with HDMI out and HDMI in. So we would connect from our source output into the HDMI sync input, and then from the receiver's source output back into our sync input. And we could monitor the video signal on a television display and loop through a video analyzer if required. If you had a video analyzer and you wanted to analyze the video at the same time, you could do that. So HDMI has some complex audio testing requirements. The source devices must supply the audio formatted correctly for the sync based on this EDID, and there's possible transcoding in the source. There are many supported audio formats and sample rates. If you get into some of these encoded audio formats like Dolby and DTS, there are lots of different possibilities. And the sync devices must be able to handle all of the audio formats supplied in the EDID. So the APX HDMI module greatly simplifies the testing of HDMI devices, both source and sync. Support for high-resolution audio formats, video generation and video pass-through, and the EDID control. So what I have here is a device. It's a little inexpensive device that is HDMI repeater. So it's HDMI on the two ends, and then it uses two Cat6 Ethernet cables in between. And I just bought this from Amazon. It's pretty inexpensive, $16 US, and it's a good way to demonstrate a device that's digital in and digital out. And it's also HDMI. So what I'm going to do is do a little test here with APX software. We're just going to plug one in into our sync input, one into our source output. The thing that I found out about this device is it's important which one you choose as which. It's not interchangeable. So one end is labeled sender and the other end is labeled receiver. And hopefully I didn't get them backwards. So what we would do is in the input-output configuration, we would choose output as digital HDMI source. And on the input configuration, we would choose HDMI sync. And yeah, so we can see here we have linear 8-channel layout. Actually, I'm going to switch over to sequence mode. It looks a little nicer in sequence mode. So again, I'm going to switch to HDMI source, HDMI sync. And if I look down at the indicators here, I can see I'm HDMI layout 1, which is 8 channels, 48 kilohertz. And on the input side, the signal is locked. It's showing as PCM at 48 kilohertz. So I can just turn on the generator, and right away I'm generating a very pure sine wave, 24-bit resolution, minus 20 dBFS on 8 channels. So on the HDMI source settings, there are some things we can do. We can disable dither or enable dither. We can change the bit depth. You'll see the noise floor creep up as I do that. And just as I showed you on the during the slides, you know, we can play with the video resolution, and we have all of these controls. Now, one of the things when you're testing digital audio, and a device like this that is digital in and digital out is kind of unique because ideally it should be what we call bit exact. In other words, every bit that is transmitted is also what's received. There's no modification to it whatsoever. And some devices are bit exact and some are not bit exact. Now if you, we have a test for bit exactness, and we can, it's shown over here as error rate, and it doesn't work with the sine wave, but we have a special signal inside of the APX analyzer called bit test. And if you look at the bit test signal, it's a pseudo-random noise signal, but it's a pattern, a sequence of bits that the generator generates a certain sequence, and the analyzer analyzes the sequence, and the analyzer knows each bit that's coming in. So it's able to compare the input stream to the output stream on a bit-by-bit basis. And you'll either get 0%, which is perfect, that's what you want, or you get some number that's not 0%. So if it's anything other than 0%, like let's say you had a sample rate converter, you know, if it changes the sample rate, it's not going to be a bit exact. There's no way it can be bit exact. But if the interface is bit exact like this is, then there's no need to do any audio quality tests, because if the bits match perfectly, then the audio is going to be just as good on the input as it was on the output. and the device, there's no point in doing any further audio tests. So one of the things you can do on the interface here is you can monitor the signal, and you can play with things on the output side, like for example, what happens if I change the video resolution? If I go to 1920 by 1080 at 60 hertz, you'll see that it, you know, as I'm changing it, the bit exactness changes from 0%, but it right away goes back to 0% errors. So it's still bit exact. The other thing I can do is play with the color depth, and I'll get the same bit of information. So at one of these plug fests that I went to, I was testing with a gentleman who had an HDMI repeater, and they could send an HDMI signal over Ethernet like this for several hundred meters. And we connected up his device and did this bit accuracy test, and it would pass the test 0% errors at 8-bit color resolution, but we went to the higher video formats and the higher resolutions, and it was no longer bit exact. So that doesn't mean it's terrible, it just means that it's not bit exact, and if it's not bit exact, then you need to go and do some diagnostic testing to figure out what's going wrong in the signal. And there are some tools that we have for that. We can look at the bits display. So if a signal, this shows the number of active data bits, the active bits or the data bits. So when you look at the data bits, of course, it's pretty hard to see for a random signal like this. But if you look at the active bits, you can see the bits from the least significant bit all the way up to the most significant bit. So 24 bits of audio. And if I go in here and change the bit depth, you should see this display change as I change the bit depth. So some of the devices that I've tested with at these plug fests, they were digital in to digital out, and we went ahead and did this bit test measurement, and we found out that it was not bit accurate. So we would come in here and look at excuse me, look at the active data bits, and we found out it was supposed to be a 24-bit device, but it was only using 20 bits. So there are kind of some nice features for being able to check for problems. The other thing we can do here is there's another signal called walking ones and walking zeros, and here it just toggles the bits. We're at a sample rate of 48K, so every 200 milliseconds we're toggling the active bits. So you can look at the data bits here. So that's the walking one signal. We have the walking zero signal. And then you can also use a constant value, and you can just type the value in hex here, and that's the value you want to see. So it's another tool for looking at which bits are active on the digital input and output channel. All right, so let's go back to this graph here. Oh, we want to turn on the sine wave. And here I can easily change from layout 1, which is 8 channels, to layout 0, which is 2 channels, or vice versa. Yeah, layout 0 is 2 channels. So now we're just seeing 2 channels of audio. So we're just going to cover ARC, which is for the audio return channel. ARC was added in HDMI 1.4a. So this is audio data going over the HDMI cable in the reverse direction from the main signal. And there's really only one use for ARC. It's when you have a television connected to an AV receiver, and if you're streaming in a wireless signal over the air, like a broadcast signal, and you want to send the signal to the receiver over the same cable, you can use what's called the audio return channel. It also provides for high resolution audio up to 192 kilohertz, 24 bits, and only 2 channels uncompressed. It's standard on most new consumer audiovisual equipment. So this is, as you can see here, you're tuning in a signal over the air. you're also connected via HDMI to your receiver. And before you had the audio return channel, you would have to run a cable like SPDIF or optical between the television and the receiver. Once the audio return channel was added, you can now send that audio signal back over the HDMI cable in the reverse direction from the main signal. So when we're testing ARC on our device, we have to use the aux-in connector and the aux-out connector. So you would connect the device under test, typically a home theater receiver, to our ARC transmit port. And then a television would typically be connected to our ARC receive port. And then we also have the ability to loop back the ARC connection within the software, within the analyzer. So as I mentioned, the aux-in connector is used for ARC transmit. The aux-out connector is used for ARC receive. And this generates linear 2-channel PCM 24-bit audio. It can output pre-encoded audio waveforms in Dolby and DTS formats. And we can analyze 2-channel linear PCM. So inside the APX software, under signal path setup, you would choose your connector to be HDMI ARC transmit. You would set the sample rate, and you have the settings button with similar settings as the HDMI. On the input side, you would choose the HDMI ARC receiver and similar controls. So the ARC transmit settings are the ARC link can be negotiated or the audio forced on. The ARC mode can be set to common mode or single mode. You can also control the sample rate, enable or disable dither, and you have control of the status and user bits just like you would over the other digital audio formats. You can edit the EDID, and you can send CEC commands. On the ARC receive settings, you have common mode or single mode, bit depth, and you can send CEC commands. The CEC controls allow you to send from and to, and the commands you can send are a ping or a custom operation code and operands, or you can send a message. When you're connected in ARC, the status bar looks like this. So the output is shown as HDMI ARC, and it's either on or off. The input is HDMI ARC. It shows the data type. This is PCM, and the input sample rate. So ARC is very simple. It just eliminates the need for a separate SPDIF cable returning from a TV. It generates linear 2-channel PCM 24-bit audio. It can output pre-encoded audio waveforms in Dolby and DTS formats, and we can analyze 2-channel linear PCM audio. And it's also standard on most new consumer AV equipment. Here's an example of testing a receiver. So the ARC transmit source to analog unbalanced outputs. So you would connect the ARC transmit to the HDMI source connector, and then connect the analog outputs from the receiver to our analog inputs. For testing a television, you would take the HDMI input connection and plug it into the ARC receiver port on the APX analyzer. And then here's testing a television in pass-through mode. So here the HDMI input from the television is connected to the HDMI source on the receiver and going to our analog outputs. So in this case, you would be analyzing signals that are sent over the RF interface, not from the analyzer. We're not using the output of the audio analyzer at all. I think that's it for ARC. Any questions on ARC? So something else I could show you here in the software is when we're in the HDMI, there's an extra set of monitors here. HDMI metadata, and so if I go to the source control, and then I can undock this panel, and you can see if I want to change things on the audio info frame. By default, they're automatically generated, but I can change this to some parameter, and it'll show up somewhere here in the audio info frame. So I can change the sample rate. Actually, it may not be here. So one of the measurements we have for digital audio testing that's quite useful is called metadata recorder. And let me add that measurement here. So what I did is I clicked the add measurement at the bottom of the navigator here, and if I scroll down, you can see metadata recorder. So the way this works is it adds a measurement that has a sweep time on it, and there are a number of fields that you can look at. So we can look at the lock status of the device, the measured sample rate, the encoded audio data type, and so on. And there's a control below the graph here where you can choose the fields that you want to look at. What's going on there? Oh, sorry, it's it's on my other monitor. So these grayed out fields have already been added to the display. I can look at the encoding, Dolby. Under HDMI, one of the things I might want to look at is N and CTS. I might want to look at AV mute, HDCP decrypting, and let's see, I've got the measured sample rate up there. So you add a number of metadata fields to the display, and then you can choose a sweep time, and let me choose 20 seconds. So this works a bit like a logic analyzer. So when I start the measurement, it's just going to record any time one of these metadata parameters changes value. So one of the ways to make it change value is I'm going to hit the start button, and I'm going to do what's called a hot plug. So I'll just come over here, unplug the device, plug it back in, and I'll unplug the device and plug it back in again. Just wait for that to finish. So it's all done. By default here, this is it's a scrolling display, so let me try auto scaling it. So here you can see we've recorded the lock status, the measured sample rate. So things only get recorded when there's a change in status. So you can see here at about, well, the sample rate was bobbling around a little bit for some reason, but here we have the data type. So you can see that it went unlocked here at about 5.713 seconds, and if you hover over the transition, I think it will show you the value. And you can see that AV mute was false. It stuttered for a little bit. It flickered between, it went true, and then it went false again, and true, and so on. So it's kind of a nice feature for debugging these metadata problems that occur between devices. You can also look at this as a data table. Let's see, I think it's here. And you can export this table to Excel if you like, and you'll get a table like this that shows the transition time and what the measured value was. So that's kind of a nice feature. Okay, so the DSIO interface is for connecting serial digital I/O devices to the APX series analyzers. It's required when the device doesn't have another interface. So this is typically used in the development process. If you have a new chip that you're working on, or you want to work on a new chip that you want to build into your device, quite often you'll get from the vendor an evaluation board that has little 2-pin headers on it that you can use to connect to the device. So it provides data and clock signals to or from the device under test. And it formats the data into the format required by the manufacturer. And it provides chip or circuit level connections. So typical applications are A to D and D to A converters, sample rate converters, I2S audio devices, and TDM devices. I2S and TDM are two different formats. I2S uses, well, in APX we have 4 data lines over which we can send I2S, 2 channels each, or we can also send TDM, where all of the channels are sent on one data line. It's used for printed circuit, audio components and motherboards, and for multi-channel converters, up to 16 channels. So currently we handle 1, 2, 4, 8, or 16 channels. We handle sample rates from 4 kilohertz to 432 kilohertz, and this was just announced I think this week or maybe last week. So there's a new release to our software, version 4.1.1, which is available for download now. We just posted it on Friday last week. And it allows sample rates on the DSIO up to 432K. So the master clock rates are up to 56 megahertz, and we have logic levels of 3.3 volts, 2.5 volts, or 1.8 volts, and bit depths from 8 bits to 32 bits. This is what the module looks like on the front panel. So there's a, uses these 15-pin connectors that I talked about this morning. So we have the transmitter output, the receiver input, and like all of the inputs and outputs on APX, there's well, except for the 515, there's a little red LED for the output side and a green LED for the input side that shows when the interface is active. We also have a monitor output and a monitor input. And these use 3.3 volt logic levels. These are the cables that we provide. So there's a cable with all of these 2-pin headers that connects directly to the headers on a circuit board. And then we have these BNC cables for the monitor output to connect to an oscilloscope. We also have this optional low capacitance cable with very short leads. A lot of times these smaller power devices cannot handle a lot of cable capacitance. So this shorter cable is available. This shows the pin-out connections for the transmitter receiver. So it's a 15-pin, just like a VGA connector, but it's a different pin-out. And here's the software implementation. So on the input-output, you would choose digital serial, and you can turn the transmitter outputs on or off. Excuse me. And then same thing on the input side. You have the digital serial connector, and you can configure the serial receiver with these settings buttons. So on the transmitter settings, it's a little bit complicated to set up these interfaces. So one of the features we have is you can create, once you've got the thing working, you can save the configuration to a file, and you can give the file the name of your device under test. Then when you come back to work on that device, you can just read in that file and all of your settings will be loaded. So we have controls for the audio format, the clocks, the frequency, the bit clock edge sync, the logic, and the timing diagram. And we also have controls for dither And here we have scale frequency by control. On the receiver settings, same thing. We have an open and save configuration, which is very handy. So basically the same as what we had on the transmitter side, except there's no frequency controls. So we have audio, clocks, bit clock, edge sync, logic, and a timing diagram. This is a timing diagram from a typical data sheet. And it's a nice feature in the APX software that you get a timing diagram built right in, so you can easily compare it to the data sheet and set it up the way the data sheet suggests. So this shows I2S or I2S, a right justified format, DSP format, and left justified. Now in terms of audio settings, we can use a single data line, which is sometimes called TDM. This can have 1, 2, 4, 8, or 16 channels. And the defined stream can be output on any of the 4 data lines. So one of the ways to use it is you can set up to 64 channels that you can generate 16 channels at a time just by switching the active data line that you're using. So it's a little bit like an audio switcher in that sense. You can also have multiple data lines, so we have 4 data lines, and each one can have 1, 2, 4, or 8 channels, and 1 or 2 channels on the first data line. You have control over which the bit direction, whether it's MSB or LSB first, the justification, left or right, the frame pulse, 1 bit or clock or subframe or 50% duty cycle, and then the frame clock you can invert or shift left relative to the data. You have the word width control, which is you can set from 8 to 128, and the bit depth control, which can be set from 8 bits to 32 bits. And then on the transmitter side, we can enable or disable dither to be added to the audio signal. In terms of clock settings, you have the master clock source. So the panel configuration depends on the master clock source and the bit and frame clock direction. So here we have internal, external, and then a difference between settings and readings. So typically in the software, when something is settable, it shows up as a white background with black text. But when it's a reading only, we're just monitoring the value, it shows up as a green text on a black background. So for settings and readings, we have the master clock rate, the frame clock rate, and the ratio of the master clock to the frame clock. Now there's the concept of slave mode versus master mode, and it really depends on the direction of the bit clock and the frame clock, whether we're sending the bit clock and the frame clock or receiving the bit clock and the frame clock. So for the transmitter only in slave mode, the bit and frame clocks are provided by the device under test. In this case, we have this scale frequency by, so you can have a fixed rate. You can enter the rate when the incoming frame clock rate is not stable. For example, when jitter is present to scale the generator frequency, or you can use the measured rate. In this case, you would use it to scale the generator frequency to the incoming frame clock rate. For example, when testing a sample rate converter device. In terms of the bit clock edge sync settings, there's outs and ins. And you can select whether the leading edge of the frame and data are synchronized with the rising or falling edge of the bit clock. So here we see the rising edge synced with the most significant bit, and here we have the falling edge in sync with the most significant bit. Then we have the logic settings, so the logic levels are 1.8 volt, 2.5 volt, and 3.3 volts. And then there's a logic on-off button, which off removes all of the output voltage from the outputs. Now, master versus slave operation. In the transmitter master configuration, the bit clock and the frame clock are going from the APX transmitter to the device under test. And in the transmitter slave configuration, the bit clock and the frame clock are coming in from the device under test to the APX. So you'll get a different display on the clocks panel depending on which configuration you're using. So this is a transmitter master clock external. So in this case, the master clock is external. It could either be coming from the device or from an external clock generator. But we're the master clock, so we're sending the bit clock and the frame clock to the device under test. Here we have the transmitter slave configuration. So the master clock is external. An external clock generator is being transmitted to the device under test, and the bit clock and frame clock are coming into the APX transmitter. This shows the receiver master clock internal. So in this case, the receiver master configuration, the clock source is internal. We're generating the master clock. We're also generating the bit clock and the frame clock to the device under test. Here in the receiver slave configuration, so the master clock source is also internal, but the bit clock and the frame clock are coming in from the device under test. This shows the receiver master clock external. So in this case, the master clock is either coming from, looks like it's coming from an external master clock, but the bit clock and the frame clock are coming from APX receiver to the device under test. And in the slave configuration, the external master clock goes to the DUT, and the bit clock and frame clock are coming into the APX receiver from the device under test. This shows a typical evaluation board connected to the APX DSIO module. So there's a cable that we supply with these two-pin headers on it. There are 4 data lines, and then lines for the channel clock, the master clock, the bit clock, and the frame clock. And then I think I showed this slide earlier, but you can see the different connection types. So the BNC cable is used for monitoring the signal with an oscilloscope. Something to be aware of here is that the signal that you're going to measure from our monitor output is not exactly the same as what's on the board. It's buffered, and it uses a Schmidt trigger, so it's going to have the same timing, but it's going to be a better quality signal than you might have on your device under test. And we also have this optional short. Well, I think this was made by someone for a special project, but we have a variant of this that we sell as well. And yeah, I showed this slide this morning under what not to do, so you can see these impaired signals, and probably a result of all of these terrible connections on this evaluation board. So you want to avoid these circuit branches. You want to avoid high capacitance cables. Don't use cables that are too long if you can, and avoid inconsistent grounding. Here's an example of a scope view of the clock and data signals via the buffered monitor output on the DSIO module. So as I mentioned, these buffered signals can appear cleaner than the true signal. So here we have the frame clock, and then the bit clock, data clock, and the master clock. Here's an example of a single channel digital to analog converter. So we have the bit clock on the top, the channel clock, and the frame clock. So you can see there's one channel period per frame period, showing it's a one-channel device. And then we have the data coming out. And what we've done here is prepared a waveform that's a constant value, so you can see a certain bit pattern showing up in the data line. Here's an example with a 2-channel D to A converter. So with the frame clock, you have 2-channel pulses per frame clock, showing it's a 2-channel device. And here, the way this was set up, there's a different constant output on channel 1 versus channel 2. So you can see these patterns of bits in the different channels, channel 1 and channel 2 and so on. Here's a third example with a 2-channel DAC using what's called the I2S format. So here we have the bit clock, the channel clock, and the frame clock. And again, you see 2 channel periods per frame clock. And then the data. So there's a constant, 2 different constant values showing up in the data as shown. And here's an example with a 4-channel digital to analog converter. So we have the bit clock, channel clock, and frame clock, and you can see 4 transitions of the channel clock for each period of the frame clock. And here we have constant values in channel 1 and channel 2, and then zeros in channel 3 and channel 4. So you can see channel 1, channel 2, and then 3 and 4 would be in this gap between signals. So that's it for the, we're going to talk about Bluetooth tomorrow. And it really, you know, with Bluetooth, it's a wireless connection and it uses a codec. So it, the standard codec that's available, and it really depends on the profile that you're in, right? There's a hands-free profile, which is low quality, 8 kilohertz or 16 kilohertz sample rate. And then there's the A2DP, stereo music profile. But the stereo music profile typically uses the SBC codec, or there are other optional codecs like aptX is one. And they don't have very high signal-to-noise ratio. Like the residual distortion is typically, the best you can get is about 70 dB. 70, yeah. Yeah, I've done some work with them. I mean, I haven't measured SNR, but the residual THD plus N would be close, you know, because it's you're measuring how clean a sine wave you can generate, right? And the best that I've been able to get with those 2 codecs is about 70 dB. So we could actually measure. I have a device here, and tomorrow, if you'd like, we can measure signal-to-noise ratio. Yeah. Sure. So most devices are either Bluetooth in and analog out, or analog in and Bluetooth out.
I mean the wireless and digital out.
Wireless, yeah.
Digital, I want to check the digital out.
Do you have a do you have access to the I2S or?
Yeah, yeah. Your equipment has DSIO.
Yeah.
So you can read the digital out.
Yeah, you could do that. I mean, I don't have a device that's digital out. I have a device that's analog out that we could test. But we have done some tests where we've connected our one APX analyzer to a second APX analyzer. So it's the same, you know, digital. It's Bluetooth in and Bluetooth out, basically. But it's 2 systems, right? But I can pretty much tell you that the best you're going to get is, it's not that great. It's about 70 dB. So I think that's all I have today. Oh, actually, I have a couple of more slides here. Let me see if I can find them. Since we had the new release coming on Friday, I wanted to just mention some of the features that are in it. So APX 4.1.1 adds DSIO support for sample rates up to 432 kilosamples per second. So previously we were able to go up to 216K, and we've had customers keep asking for higher sample rates for some reason. So the latest thing people have been asking for is 384, and they're probably going to keep going higher and higher. I don't know why, but anyhow, we can go to 432 now. So it's the same. We can do configurations of 1, 2, 4, or 8 channels on single or multiple data lines. It supports input and output sample rates up to 216 K samples per second for 16 channel configurations on a single data line. So, you know, there's a bandwidth limitation. When you get very high channel counts, you can't go as high a frequency. There is a constraint with our generator. So the maximum sine wave frequency we can generate is 108 kilohertz. And that's a limitation inside the instrument. There's a little power PC chip that generates the signals, and it can't keep up with the so the clock sync on the back runs into trouble. So the generator is limited to 108 kilohertz. So this just shows some screenshots of the system setup for 432 kilohertz. So here we have 8 channels being generated in DSP format. It's probably just a loop back, but you can see the sample rate here, and then 8 channels of audio being generated, and the bit depth is 32 bits. So 432K sample rate at 32 bits. That's really quite good. And then 216 kilosamples per second for 16 channels. And here the bit depth is limited to 16 bits. So if you want to go 16 channels, you have 216K at 16 bits.